Hopefully it wasn't as bad for you as it was for me. I didn't switch any of the slides out at this point, so if you've got questions about any of those slides in particular. Yes, no. So this just summarized the results. We can have acids reacting with our alcohols, activating them for nucleophilic attack, so we can get a substitution reaction. Whoops. So we've got substitution in this first case. If we don't activate it with an acid, we can activate it with a very, very positive sulfur atom, and we can still get a substitution reaction. And then the last one that was on here was activating the alcohol in kind of the reverse sense. Instead of having the alcohol act as a leaving group, we turn it into the nucleophile. So we run an acid-base reaction first, and then have it act again as a substitution, but this time our alcohol acts as a nucleophile as opposed to leaving groups in the previous cases. Okay? Everyone was good with that? Okay. So looking at alcohols as nucleophiles, they have those lone pairs. Those lone pairs can react with positive species. We can make them react more frequently or with a higher effective rate by making them negatively charged. So we make our alcohol act as an acid by reacting it with a base. Okay? We have to make it a strong base. We evaluated what bases were best. As far as you're concerned, sodium metal or sodium hydride are going to be your two best bets. They both will do the same thing. So we've got sodium hydride here. Sodium metal would be shown as Na solid. That will react with the alcohol, and one of the byproducts would be NaH. So it goes through and it reacts with twice the efficiency of sodium hydride. Okay? That is an S in parentheses for solid phase. Okay? That sodium is different from the sodium that we're used to seeing, because typically when we think about sodium, we think about it being useless as far as chemistry goes. But that's not sodium solid. What is that? That's sodium ion. That would be shown as Na+, or we might even see it as sodium bound to something like hydroxide. We have a metal and nonmetal bond. There's our metal and nonmetal. So we have an ionic bond. Again, that gives us Na+, okay, our sodium ion. Sodium ion is effectively useless. Sodium metal is extremely reactive because it wants to become sodium ion so readily. So it'll shuttle off those electrons pretty fast. Okay? So that's our good base. Is it going to work? Oh, it will work. So we can have our alcohol. For some reason, I can't get my acids and bases straight. We can have our alcohol act as an acid in these cases to make it a nucleophile. So we went through a long, drawn-out example of alcohols reacting with hydroxide versus alcohols acting with sodium hydride. We saw the reversibility that we get with hydroxide, and we see no reversible reaction when we react it with sodium hydride. All right? And then mentioned that we had sodium metals doing the same thing. Okay? We look quickly at the elimination reactions, E1 versus E2. As far as alcohols go, they're all going to involve the same first step. To do an elimination reaction with an alcohol, we must have the alcohol act as a base first, okay, and donate electrons to a hydrogen ion to make, geez, how many carbons were in that? Our oxonium ion. We need a good leaving group. So if we're going to do an elimination reaction with an alcohol, it must react with an acid first, okay, so that we now have that good leaving group. If we limit the presence of a nucleophile, we can force an elimination reaction to occur by adding heat. Okay? And to do that, we'd add heat to weaken the hydrogen bond, kicks and breaks out. Which mechanism did this one go by? E1 or E2? E2 because, what's that? We could go with it happens all at once. If we take a look at that second step with all my arrows on it in there, okay, I've got everything happening to generate, oops, too many carbons, to generate the terminal double bond. So we could do it based on the mechanism shown. The mechanism says it's E2. What else? What other evidence do we have that it would be an E2? There's no base. Okay, no strong base. We've got the weak base of the alcohol. Okay, we're actually under acidic conditions, so there's no strong base to push E2. We don't have a nucleophile at all. If we had a nucleophile, we wouldn't see an elimination reaction. We'd see substitution. This one's tricky. It's primary. Okay. E1 elimination reactions require the tertiary or secondary substrate. They won't move through our primary mechanism because that gives us a carbocation, a terminal carbocation, or a primary carbocation. We can't do that. Okay? So this reaction is an E2. Okay? And if we went back to our summaries of these, and we looked at our E2, our substrate pattern says we would expect tertiary to go first, but we can get our primary. No way we could get a methyl. Why can we not get a methyl? An elimination results in what? It's the functional group of our product. In an elimination reaction. It's an alkene. Okay? So a double bond. Can I get a double bond on one carbon? No. Okay, so that zero area shouldn't be there. We can get a primary to react in the elimination. It's not as favored. Okay? To really get that elimination to occur with a primary substrate, we have to make sure there's no good nucleophile. Otherwise, we would see that substitution. Okay? With the E1, we would not see any eliminations out there because we can't form that primary carbocation. Okay? And a blank slide. So now we're going to move on to our reduction and oxidation reactions. We've seen a little bit of this kind of summary stuff from the alkene chapter. I believe there were some homework questions looking at it. So we're going to talk about those in a little bit more depth now. From general chemistry, hopefully you remember the loss of electrons is oxidation, and the gain of electrons is reduction. We can even come up with nice mnemonic devices to memorize that, except that's not going to be particularly useful when we move into organic chemistry, because we don't really look at the exchange of oxidation states. Okay? So the changing of an oxidation state is different from the changing or passing of electrons. Okay? So we can't correlate those definitions as well. So when we go into organic chemistry, what we're going to do is try and find our reactive site where things are changing. And it's typically going to be a carbon atom, but it could be other atoms, but mostly we're looking around carbon. And we're going to evaluate how the bond structure changes. Okay? The easiest definitions are looking for hydrogens and oxygens. Okay? So if we're going to look at an oxidation, oxidation is referring to an increase, hopefully that shows that, of oxygen bonds. Okay? Here it shows electronegative bonds. Well, oxygen is electronegative, so it makes sense. So the definition of oxidation ultimately came from reacting with oxygen. Okay? So we're increasing those oxygen bonds. That definition is a bit narrow, which is why we shift to increasing the number of electronegative bonds. The other thing we could look at is decreasing the number of hydrogen bonds. Not the force, but actual hydrogen atoms being bound to the structure. Yes?
So you can't have both of these at the same time, right?
We can have both of these at the same time.
The homework said And it said neither as oxidation.
I would have to go to the problem to specify it, but you can have these both occur at the same time. You have to make sure you're careful where you're looking, though. Reduction, we can look at the increase in hydrogen bonds. So ultimately what we're trying to do is replace those oxygen bonds. The easiest thing to replace with would be hydrogen. So if we increase the number of hydrogen bonds, we're looking at a reduction, or the decrease in electronegative bonds, okay, or the decrease of oxygen bonds, okay. So those are our primary patterns to look for. We can get all sorts of more complicated reactions and problems up there. Your textbook probably asks you a few of those. I tried to keep them relatively simple here. Okay, so let's go ahead and take a look at a few of these examples to see if we can figure out if we've got reduction or oxidation. Okay, so what's happening in that first step? What things are changing here? Anybody notice any differences? We've lost hydrogen. Anything else? We gained an electronegative atom. So loss of hydrogen, increase of electronegative is oxidation. Loss of hydrogen is an oxidation. So this would classify as an oxidation reaction. Okay. For this to occur, there has to be a reduction with it. We typically ignore that half of it. Why? Why do we only look at this as an oxidation reaction and not, as we should have learned in Gen Chem, a redox reaction? You get the right, well, that works. If we looked at the reverse reaction, we would expect the reduction. What class was this again? It's organic chemistry. We really only care about the organic species. Okay? The other species that's being reduced here is probably some metal or some other species in solution. Okay, so we don't care about that one because it's not organic. What happens in our next reaction? Left to right. I don't want to jump directly to the answer yet. I want to know what atoms are changing places. What's that? We lost a hydrogen. I probably didn't want to hear it. What else happened? We did form a double bond. Okay, that one's a bit tricky. So we did increase something, but what did we increase? We added that new bond between what? To what kind of an atom? To carbon. Well, it's not really an electronegative element, right? So we have a little problem with that. Should that count as increasing an electronegative element? What's the hybridization? We'll go with blue to make it different. Of that carbon versus that carbon. sp3 versus sp2. What changes when we decrease the hybridization? The electronegativity also increases. Okay? So as we move from an sp3 atom to an sp2, we have actually increased the bonds to an electronegative atom. Okay? Because we went to an sp2 carbon from an sp3. Okay? So we do have a plus sp2, I guess, in this case. So if we've decreased hydrogens, increased electronegative, we're looking at oxidation. Okay. So what I'm trying to specify is looking at those definitions. So we looked at increasing or decreasing hydrogen atoms or increasing and decreasing electronegative atoms. Okay? So our definition goes around electronegative atoms, not necessarily oxygen. Okay? So we can see that we definitely lost hydrogen. Okay? But then what increased in its place? Okay? And when we look at the atoms, we don't really see the atoms change necessarily. It's still carbon and carbon. But what did change was the hybridization. Okay? So I added a new bond. Okay, that pi bond is new. So that is effectively a bond to an sp2 carbon that wasn't there before. Okay, it was an sp3 carbon. Did the electronegativity change to go from an sp3 to an sp2? Yes, an sp2 is more electronegative than an sp3, so effectively I increased the number of electronegative atoms in that position. Okay, so I did do an oxidation reaction. Hope these all aren't oxidation reactions. Okay, let's take a look at this next one. Should I be erasing these as we go? Or leave them up there? Leave them? Okay. Next one. What changed? I lost chloride. And I gained effectively an OH, but we can say an oxygen. Why would we only look at the oxygen, not necessarily that hydrogen? We'll pick the atom where our chemistry is occurring. It's that carbon. The bond that actually formed there was to the oxygen. Okay? So I lost an electronegative atom, and I gained an electronegative atom. What's the result? We won't get into it that far either. They're both more electronegative than carbon. So what's our result? Both happen at the same time, they cancel each other out, and we get neither. Right? Next one. What the heck? Apparently I like oxidation. What changed here? Where did I lose the hydrogen? One should be super, super careful with this. Which hydrogen did I lose? Is it the one on the oxygen relevant? No. Which hydrogen did I lose? I lost one off of the carbon. So I've lost hydrogen and I gained oxygen. We're looking at an increase in oxidation, so we're looking at oxidation reactions. Okay? Is this too many examples, or should we keep going? Okay, let's try the next one. Just checking. Yes?
Why do you say that you gained an oxygen when there's still an oxygen on both of them?
It's gaining an oxygen bond.
Oh.
Okay, so what we'll do is look at the bonds changing here. So we may not necessarily increase the number of oxygens, but we're increasing the number of bonds. Good question.
Did you also say the sp3, sp2?
I kind of wonder that. I would ignore that effect because the oxygen is so much more drastic. So I'm going to defer to, I'm not going to answer that question. Okay. Other questions? Okay, so, whoops, I'm already there. What happened in that next reaction? We lost an oxygen. I heard someone saying gaining. What did you gain? And where did you gain it? Where's the hydrogen gained? We've got that implied hydrogen on that aldehyde functional group, which means, what type of reaction did I do here? Got a reduction. I don't know why I decided to write that out. Okay, hey, the first reduction, look at that. Okay, last one. Anything else happen? Good, I actually wanted to hear that. Gained another oxygen. What else? I lost hydrogen twice. So overall, this was an oxidation that happened twice. So it was a double oxidation in this case. Okay? Because I increased the number of oxygen bonds twofold. I've started with one oxygen bond, I now have 3. So I've increased the number of oxygen bonds by 2, and I decreased my hydrogen bonds by 2 as well. Because if we take a look at our reactive carbon again, it's lost both those hydrogens in the process of this reaction. Okay? Does that make sense? Okay. You might see more complex problems in the textbook. I would leave you to refer to the textbook to decide what's going on with those and help you out with them. These are the types of ones that I'll ask you along these formats. Okay? Fun thing about showing you these problems is I could show you the reverse just as easily. Okay? And now I've quickly changed the question into something entirely new and different that no one will recognize. Okay? It's not supposed to be kind of a joke, right? Okay? The idea is that you count, look for those differences, evaluate, and decide what changed. Okay? And as long as you've got those marks or those occurrences that have changed recorded, hopefully you'll be able to identify reduction or oxidation, whichever direction it goes. Okay? Questions about that? Okay, so as far as responsibilities go, I do expect you to be able to identify reactions as oxidation or reduction. The next part is looking at the individual reagents that allow each of these transitions to occur. Okay? And that's a little bit trickier. Some of them you're responsible for, some of them you're not. You have quite a few oxidation reactions that you are responsible for. Okay? You've got some from the alkene chapter. Converting an alkene into a diol is an oxidation reaction. You've increased the number of oxygen bonds. Okay? So you have a lot of possible types to evaluate as far as oxidation. And we're going to look at 2 more reagents today. Okay? Looking at alcohol reduction, or sorry, oxidations. You've already seen one reduction, and it's the only one that I think, the only reagent that I think you're responsible for. Yeah, I think that's the only reduction reagent you're responsible for is hydrogen. Okay? Adding hydrogen gas to a reaction, that requires a catalyst, if you remember that from your alkenes. You're looking at platinum, palladium, or nickel. Okay? So that's your only reducing agent that you're responsible for. Okay? And I'll look a little bit closer at your reagents to see if there's another one, but I think that's it. Okay? Any questions about that stuff before we start jumping into the reactions themselves? Okay, then let's do it. So before we push too much further into the reagents, we want to get an idea of overall what can happen as far as oxidation reactions go. Since we're concerned about alcohols, we want to be concerned about all of the possible oxidations that can occur to an alcohol. So one of the things when we look at oxidation, what has to happen? There were 2 things that need to occur for oxidation. What's that? We need to increase electronegative bonds. In the case of looking at alcohol reactivity, more than likely that electronegative bond is going to be oxygen. What was the other thing that could happen? Decrease in hydrogen bonds. Okay, so we should be trying to evaluate both those things as we kind of process through these things. Okay? And for the oxidation of alcohols, both of these things must occur. We must both increase the number of oxygen bonds and decrease the number of hydrogen bonds. If we can't do one of those, what happens? It doesn't occur, and our oxidation ceases. Okay? So we've got 3 different types of alcohols, our primary, secondary, and tertiary, which we've already talked about. So it's where our alcohol is attached, how many carbons are attached to it. If we look at a primary alcohol and I want to oxidize it, okay, all I need to do is increase the number of oxygen bonds and remove a hydrogen bond. So what happens? I move up to a new functional group. Okay? So if we draw out our hydrogens so we can see them, there are 2 hydrogens on that carbon. I get rid of one and replace it with an oxygen bond. I now have a new functional group. What is this functional group? What was that? Carbonyl refers to the carbon-oxygen double bond. What is the functional group as a whole? Does that help or hurt? There it was. We have an aldehyde functional group. After a single oxidation step of a primary alcohol, we stop at the aldehyde. Okay? If we continue to oxidize, because I still have a hydrogen there, so I can take that hydrogen off and swap it with a new oxygen bond, I can move to yet another functional group. This functional group is now the carboxylic acid. Okay? So alcohols could be oxidized twice depending on the chemicals we use. Okay? When we move to the secondary alcohol, we still have that one implied hydrogen there. So we can go ahead and try and oxidize it. As we oxidize it once, we remove that hydrogen and we increase the number of oxygen bonds, and we're left with what functional group? Ketone. Okay. How many hydrogens are on that center carbon now? None. Okay. Which means if we don't have any hydrogens to remove, we can't oxidize any further. At least not just undestructively. If we attempt to oxidize further, we're going to destroy the compound. Okay? Literally break apart carbon-carbon bonds, turn it into CO2. So we could potentially oxidize a lot further, but that involves lots of destruction. We tend to avoid destruction when we're making products. Okay? So we stop at our ketone with secondary alcohols. When we move to a tertiary alcohol, how many hydrogens are attached to that reactive carbon? 0, which means, can I oxidize? No. So a tertiary alcohol will not react in an oxidation reaction, and you're left with the starting material. Nothing occurs. Okay? Yes?
So you're saying with alcohols in general, if you don't have alcohol, if you increase hydrogen and increase the electrons, it won't happen?
Yes.
And that's just for alcohols or?
I am not familiar enough with my redox reactions to say it's applicable to all things. It's probably applicable, but
So if the ketone is still oxidation, because you're adding the bond to get oxygen?
you're still removing a hydrogen and you're increasing the oxygen bonds. You're not adding another oxygen atom, you're increasing the bonds.
So the extra bond is adding as, increasing electrons.
Yes. Okay. How do we know that those red carbons that I went through with the starting materials, let's go through and label them blue now so they stand out a little bit more. When I asked for reactive carbon, did anybody question why I picked that carbon? That's the one that's attached to the alcohol. That's going to be our carbon that's most reactive. When we're going through the reduction or oxidation reactions, that's going to be the one we're concerned about. So you need to be able to zero in really quickly where the chemistry is occurring and try and apply your definitions appropriately at each of those positions. Okay? Make sense? Okay, so let's look at a couple reagents that can allow us to do this. Make sure I don't break the computer. Jinx myself. Okay? With our reduction and oxidation reactions, we ultimately have two oxidizing reagents that you guys need to worry about when it comes to alcohols. They react very, very, very similarly. As far as a mechanism goes, we'll look at the mechanism for chromic acid for just the oxidation of the alcohol. We'll kind of leave it at that. We won't look at the others. Okay? So chromic acid takes on a variety of forms. So you may see it in all of these possible formations, and I'm pretty sure this needs to be CrO4. So that would be chromic acid. The next one is potassium dichromate and sulfuric acid with a little bit of heat. What happens then is the structure falls apart and forms chromic acid. So it's effectively the same reagent. You're still dealing with chromic acid in all of these cases. Okay? So make sure that you're aware of that when you're trying to evaluate your individual reactions. So that should be, again, 4 for those. Okay? So the fun thing with chromic acid is it's a really, really strong oxidizing agent, and it's going to fully oxidize all alcohols as long as there's enough hydrogens to remove. So if we start with a primary alcohol, we're going to completely oxidize as long as there's hydrogens. Okay? So the alcohol had 2 possible oxidation steps. Chromic acid will go through both of those in a single bound, and the product of that reaction takes us to the carboxylic acid. Okay, right away. We do not get to isolate the aldehyde when using chromic acid. Okay? If we start with a secondary alcohol, okay, secondary alcohols quit after 1 oxidation in any case, so chromic acid will take it to the ketone and it just kind of stops there. Okay? So the big difference between these 2 reagents, and I'll keep coming back to this or harping on it, is that chromic acid will push, that's supposed to be a star, our primary alcohol to a carboxylic acid. Okay. Pyridinium chlorochromate, okay, is a slightly more complex structure. You could remember that name if you'd like, or you can just remember PCC. Because that's how you'll see it in the literature, and you'll probably see it that way in your textbook as well. Okay? I prefer to think of it as a different term. The PC, I tend to think of as politically correct chromic acid. Okay? What do I mean by that? It's a much milder reagent. Okay? We're trying to be politically nice and not offend anybody, so the oxidizing agent will stall after a single oxidation. Okay? So if we start with our alcohols, and PCC will stop at an aldehyde with a primary alcohol. Okay, so we move only to the aldehyde. If we have a secondary alcohol, it's still going to go to the ketone. It's still active enough to do that single oxidation step, but it can't take anything any further anyway. Okay? What if you start with an aldehyde and you add PCC? And PCC. I heard some people saying, hey, it does 1 oxidation step, right? It should take it to the carboxylic acid. Okay? No. It's not active enough to react with the aldehyde. That's why when it reacts with our primary alcohol, it stops at the aldehyde. If we add PCC to an aldehyde and it takes it to the carboxylic acid, when I add PCC to an alcohol, it should take it to the carboxylic acid as well. Okay? So an aldehyde, when mixed with PCC, does not react. And we don't see that oxidation step. Okay? So PCC will only react with our alcohols and only stop at the carbonyl. Okay? It won't push any further than that. If it's a terminal or a primary alcohol, that's when we'll get the aldehyde. Secondary, we'll get the ketone. Okay? Kind of makes sense with those? Okay, what part doesn't make sense?
No reaction. I'll just try to mention it again.
That's trying to oxidize it a second time. No hints?
Way back there doesn't make sense.
What's way back there? This has nothing to do with 2 weeks ago, so that I can't help you with that. Okay. So these are the reagents, our two new oxidation reagents. We've got chromic acid and PCC. Okay. We're going to go through a mechanism for the primary alcohol reacting with chromic acid and stopping at the aldehyde. It's very similar to the mechanism with PCC. And it's a very subtle difference between the two as to why we don't continue beyond that. Okay, let's see, I'm pretty sure I need a blank slide for this. Oh, nope, I gave it to myself. So let's start with our primary alcohol. Okay, and our chromic acid. It's chromic acid. Oops. Okay, so we got a lot of bonds to that chromium atom in the middle. We're allowed to do that because chromium is special. Why is it special? Where is it in the periodic table? It's in the middle. We're looking at the transition metals. It's large enough that we can deal with their d orbitals, and we can end up expanding the octets of those atoms. Okay? So what can you tell me about that chromium atom? Any idea what its charge might be? Partial or otherwise? It's probably really, really positive. Why? All of the electronegative oxygens attached to it. Okay? How could we stabilize that positive atom? What does a positive atom need? Do we have electrons? Okay? And we can donate those electrons over to our chromic acid. This really starts to push its octet, and so it gets a little bit irritated and starts to shuttle off a leaving group with water. I'm not going to be too concerned about the exact mechanism on that, but we end up kicking off water from our structure. Okay? And we end up with kick off a lot of water, or a lot of hydrogens. Okay? Does our oxygen want to be negative? Or our oxygen want to be positive? No, so we can pick up some of those electrons. Whoops, I didn't want an eraser. I'm totally running out of space very, very fast. Sorry. Draw this out. Oh, totally cramped in there.
What is that down on the bottom? Is that a hydrogen?
Yeah, that's an OH. Okay. Chromium still is very, very, very positive in this case. Okay, we still have a lot of electronegative elements attached to it. Okay? So it's going to want to steal some electrons from something somewhere. Where's the source of electrons? We can start to steal them from the oxygen. But wait, what happens to the oxygen? Now it becomes extremely positive. Does oxygen want to be positive? No. So what happens? Could try and take them back, or it can take them from somewhere else. While carbon's not a bad idea, if we take them from the carbon, we end up breaking our structure. we can instead take them from a nearby hydrogen. What's the result? And our chromium picked up a pair of electrons. Okay. So what we've ended up doing is shuttling electrons back and forth between these atoms. That chromium acts as an intermediary to shuttle the electrons. Okay, this is not a mechanism I expect you to be responsible for. It's one that I expect you just to look at and kind of get a feel for what's happening. Chromium will accept the electrons from our alcohol, creates an unstable species. That makes the hydrogen on the carbon next to our alcohol extremely acidic and can be pulled off in the course of the reaction, forming our double bond. Okay? So that metal catalyst helps to really activate our structure, allowing it to become acidic enough to form the double bond. Okay? It looks a bit convoluted, and it is, but it's not that big of an issue. What I want you to do is understand that your electrons, where they're coming from, and how you can get this reaction to occur. Okay? It has to be something like chromium to help polarize that oxygen, start to pull electrons away from it in that last case, because without that atom, we don't make this bond, okay, our carbon-hydrogen bond, and that last step, acidic enough to have the electrons pull towards the oxygen. Okay, and that's where our elimination step occurs. We lose the H plus into the solution, and we generate our aldehyde. Okay? The big difference between chromic acid and pyridinium chlorochromate is ultimately the solvent that they're in. Chromic acid is is dissolved in water. Okay? What we're going to look at after exam 3 is one of the properties of water, and in particular, carbonyl compounds. What can you tell me about the carbon of the aldehyde? What's that? It's sp2. Good. What else? As far as reactivity. Is it negative? What's it attached to? It's partially positive because it's attached to that electronegative oxygen. How can we stabilize a partial positive atom? We can take the partial negative of water. That can react with the carbonyl. That intermediate can go through a chromic acid or oxidation again to generate the carboxylic acid. Okay? That's how we moved the acid. It's really the presence of water that allows for our acid formation. Okay? Without that water, we don't get that step. We don't get the next oxidation. Pyridinium chlorochromate is... Ooh, does anybody know what pyridinium looks like? No? Okay, then maybe I can get away with this. Pyridinium, nitrogen. I think that's pyridine. Lone pair on that nitrogen. Based on chapter 10, what can you tell me about that nitrogen atom? What functional group is that? An amine. Amines act as bases. Chromic acid is an acid. What happens? Picks up the hydrogen, and we end up generating this species, pyridinium. Okay? So pyridinium chlorochromate, the only reason that pyridinium is, or yeah, I think I'm saying that right, is in there is because it's the solvent. We get rid of water. This compound we wouldn't expect to be soluble in water, so we can limit the presence of water. By limiting that presence, we can't get that secondary oxidation step. Somebody just look up pyridinium. Really? Oh, nice. Happens every so often. Okay? So our big difference with PCC is that we don't have water. Without the water, we can't get that secondary oxidation step. Okay? Again, not as big of an issue, but I just want to make sure you're aware of it in case it shows up later. Okay? Darn it. Questions about our oxidation reactions? Okay. Last thing that we'll do is look at reduction reactions. And by looking at those, ta-da! Also, just so you know, whenever you get an answer right, in general, I found that it makes you feel a lot better if you say ta-da afterwards. Okay? It seems to be increasing people's moods. Okay? So give it a shot, we'll see how it works. Okay? So if we're going to do a reduction, pretty much the only reagent that I could remember when putting these slides together was looking at hydrogen with a palladium catalyst. So as an example, let's start with the ketone. Whoops. And let's add hydrogen over palladium. What do we get? Should look kind of familiar. Like maybe something from a quiz. From the nomenclature part of your quiz. Hydrogen reacts with double bonds. So we'll add a hydrogen to each atom of our double bond. What do we get? A secondary alcohol known as isopropanol, or 2-propanol, or 1-methyl 2-ethanol. Sorry, 1-methyl ethanol. Okay? So as long as you've got a carbonyl, you can react that with hydrogen and palladium. It will reduce it and just add hydrogen across that double bond, just like we did with our alkenes. Okay? Questions about that? You need to know the mechanism for this one. Really? Anybody know the mechanism for that one? No, let's try that again. Well, you're not responsible for the mechanism for this. We're just adding the hydrogen across that double bond. Do we have a stereocenter there? No, at least not yet. If we added an extra carbon, that would be mean. But let's be mean just for the moment. Why not? Do we have a stereocenter now? Yes. What should we specify? Wedge or dash? It's going to be both. Why is it going to be both? No. The hydrogen molecule can react with the pi bond either from above, pushing the alcohol down, or it can react with the pi bond from below, pushing the alcohol up. So depending on how the alkene or our carbonyl reacts with our platinum surface, palladium surface, we might see different enantiomers. How could we specify that? Our answer here? Shortest way? That works. There's a shorter way. Because I think I said it. You go with the plus minus. Longest way, wedge, and dash. Okay? Questions about that? Okay. So after all of that, guess what? We are finally done with the alcohol chapter. Okay. So, we've got a spider diagram up here showing all of the reactions, or I at least tried to get all of the reactions that involved alcohols. There are a couple different things going on here. I tried to use that black solid line to differentiate between synthesis and then the reactions of alcohols. So from the top, we take a look at what color is substitution? We take a look at this species. What kind of a compound is that? Give me the name of that functional group. What does X stand for? What is that? It's very excellent, sure. Halogens. We're looking at a carbon-containing compound with halogens in it, so we've got an alkyl halide. Alkyl halides can react with water or a strong base to generate water or hydroxide to generate our alcohol. And what type of a reaction? Substitution. Water would be which mechanism? Hydroxide would be which mechanism? SN2. How do you know that one's SN2? Because it's strong. Water is weak, so we're looking at SN1. We could also start with an alkene. Okay, what can we do with alkenes? Can react them with an acid followed by our nucleophile of water to generate our alcohol. In what type of a reaction? It's an addition reaction because we added to the double bond. If we lose a double bond, we're getting addition. If we get a double bond in our product, that's elimination. Okay? So we can do that standard addition reaction, or we could try and convert to the diol. Oh, I should not have written over the top of that. We can convert to our diol using those two reagents, either the permanganate, and you should specify cold and dilute, or our OSO4 followed by that sequence of reagents. So it would be two steps. Okay, that gives us a diol. So we get two alcohols. We could also react with mcPBA, which gives us the epoxide. The epoxide can ring open when reacted with acid or base to generate a diol as well. One thing I do want to note with that, and that's what this is supposed to be saying here, is that the stereochemistry when reacting with mcPBA with water versus doing the permanganate, you get different products. Permanganate and the osmium tetroxide, or OSO4, generate what kind of a diol? Cis. We get the cis diol. When we do the mcPBA, we'll get our trans diol. Okay? So the stereochemistry does change depending on how you go about doing it. After that, we get all the individual reactions of our alcohols. We can have our alcohol act as an acid and react it with a strong base, such as sodium hydride or sodium metal. So what we'd be doing there is an initial acid-base reaction, such that we could then follow it up with a substitution with an alkyl halide. What type of substitution mechanism would that step be? SN2, because our alcohol is negatively charged. We now have a strong nucleophile.
What is the green supposed to represent?
Yeah, I didn't really have a good option for that. We're going to call that acid-base.
Okay.
So green will be our acid-base reaction for the moment. Okay. We could also have the alcohol act as a base. So react it with an acid generate a really good leaving group. That leaving group can either act in a substitution reaction. That substitution reaction would have to be SN1. We can't pull off the SN, that's not true. That could be SN1 or SN2, depending on our conditions, the strength of our nucleophile. Okay? Or we could do the elimination reaction to generate our alkene. We've got another substitution reaction with our thionyl chloride. What's the special circumstance with thionyl chloride? It maintains stereochemistry through the reaction. So if we start R, we end R. If we start S, we end S. We can also react our alcohol with pCC to turn it into a ketone. Okay? Because the oxidation reactions can happen with varying reagents to varying extents, and we change products when we start with a different type of alcohol, that's what this kind of supplement is for. So we'll show that on the next slide. Any questions about this slide first? This shows up bigger on the next slide. I'm about to click away. There's people still writing. Wait? No? Okay. And if we take a look at the last slide, we can take a much closer look at our alcohols. So the intent of this is to show a generic alcohol at first with different R groups, and then specify what those R groups are under each of these conditions. So with chromic acid, if our R groups are carbon and then 2 hydrogens for our R groups, we've got what kind of an alcohol? A primary alcohol. When reacting with chromic acid, we generate the carboxylic acid. When we go through in our R groups, 2 of them are carbons and 1 is hydrogen, we have what kind of an alcohol? A secondary alcohol. When we react with chromic acid, it gives us the ketone. If they're all carbons, we have a tertiary alcohol, which generates no reaction. So no change in our structure. Okay. The pCC was kind of an addendum. I don't know quite don't know if this works well, but what I'm trying to say is that if we react pCC and our R group is with all 3, again, it's tertiary, no reaction with pCC. Then move downwards, so our pCC is on the bottom half of this. Okay, so pCC kind of moves down here, kind of like a Venn diagram, right? And then our chromic acid does this. There's our overlap in between. Hey, let's color that in. Now it's purple, because the overlap of blue and red. If our R groups on our starting alcohol, we've got 2 carbons. Again, we're looking at a secondary. With pCC, that'll take us to the ketone. If we only have 1 carbon, primary alcohol, we'll stop at the aldehyde. Okay, so a single oxidation step. Okay?